Good afternoon, students. So today we have lecture number 5. Lecture number 5 on fluid mechanics. Lecture number 5 on fluid mechanics. Okay. So in the previous lecture we have studied about the different types of flow of liquids, that is streamline flow, turbulent flow, all those things we have studied, and then we have studied equation of continuity. Okay. So now next concept, so energy of a flowing fluid, energy of a flowing fluid, energy of a flowing fluid, it is energy of a flowing ideal fluid. Okay. Ideal fluid, in the previous class we have studied a non-viscous incompressible fluid. A non-viscous incompressible fluid is called ideal fluid. When an ideal fluid is flowing, it will have three types of different energy. When an ideal fluid is flowing, it will have three types of different energy. Number one, kinetic energy. Number one, kinetic energy. It is energy possessed by the fluid, ideal fluid. The energy possessed by the fluid by the virtue of its motion. The energy possessed by the fluid or liquid by the virtue of its motion is called kinetic energy. So kinetic energy of a liquid of mass m moving with velocity v is given by 1 by 2 mv square. The kinetic energy of a liquid of mass m moving with velocity v is given by 1 by 2 mv square. So kinetic energy per unit mass, kinetic energy per unit mass of liquid, the kinetic energy per unit mass of liquid is given by 1 by 2 v square, that is 1 by 2 mv square divided by m cancel 1 by 2 v square, that is kinetic energy per unit mass of liquid. And kinetic energy per unit volume, kinetic energy per unit volume of liquid is given by, kinetic energy per unit volume of liquid is given by 1 by 2 mv square, that is kinetic energy divided by volume. This is capital V volume, this is small v velocity, small v velocity. So it is mass divided by volume, that is nothing but density. So 1 by 2 rho v square. So this is kinetic energy per unit volume of liquid. And kinetic energy per unit weight of liquid, kinetic energy per unit weight of liquid. The kinetic energy per unit weight of liquid is called kinetic energy head, is called kinetic energy head. It is called kinetic energy head. So here kinetic energy per unit weight of liquid. Kinetic energy, just a liquid flowing through a ideal fluid having streamline flow has three types of energy: kinetic energy, pressure energy and potential energy. A fluid having streamline flow will have three types of energy: kinetic energy, pressure energy and potential energy. And first one I am talking about kinetic energy, that is the energy possessed by a liquid by the virtue of its motion. The energy possessed by a liquid by the virtue of its motion is called kinetic energy. The kinetic energy of a liquid of mass m moving with velocity v, kinetic energy of a liquid of mass m moving with velocity v is given by 1 by 2 mv square. Now the kinetic energy per unit mass of liquid is given by 1 by 2 v square, that is 1 by 2 mv square divided by m, will get 1 by 2 v square. Kinetic energy per unit volume of liquid, kinetic energy per unit volume of liquid, it is kinetic energy divided by volume of liquid, that is half mv square divided by v. This is volume of liquid and this is velocity of liquid, does not cancel. So mass divided by volume is density. So therefore 1 by 2 rho v square, rho is density of the liquid. And kinetic energy per unit weight of liquid, that is called as kinetic energy head. The kinetic energy per unit weight of the liquid is called as kinetic energy head, that is 1 by 2 mv square divided by mg. Weight of the liquid is nothing but mg. So cancel, you will get 1 by 2 V square divided by G, V square divided by 2G, or you can write V square divided by 2G, V square divided by 2G. This is kinetic energy head. Understood? This is kinetic energy. Second one, that is a fluid having a streamline flow will have three types of energy: kinetic energy, pressure energy and potential energy. First one, kinetic energy, is completed. Now next, second one, pressure energy. The pressure energy is the energy possessed by the liquid by the virtue of its pressure. The energy possessed by the liquid by the virtue of its pressure is called pressure energy. The energy possessed by the liquid by the virtue of pressure is called pressure energy, and the pressure energy of a liquid can be defined as, can be equal to the work done in pushing a liquid. The work done in moving a liquid against the pressure without imparting velocity. The pressure energy can be measured. The pressure energy is the energy possessed by a liquid by the virtue of its pressure, and it can be measured. It can be measured. That is, pressure energy is equal to the work done in pushing a liquid, work done in moving a liquid against the pressure without imparting velocity. Work done in pushing a liquid against the pressure without imparting velocity. That can also be called as pressure energy. That is, pressure energy can be measured as work done. That is, work done to move the liquid against the pressure without imparting velocity. So that work done is equal to the pressure energy. So now pressure energy. Now we don't know the formula for this one. So let us derive a formula, or let us consider a container having a liquid of density rho. Let us consider a container having a liquid of density rho. This container is having a opening, and this opening is fitted with this tube is fitted with a frictionless piston. Is fitted with a frictionless piston. And now the pressure, let P be the pressure exerted by the liquid on this piston. Let P be the pressure exerted by the piston, exerted by the liquid on the piston of cross sectional area A. Let P be the pressure exerted by the liquid on the piston of cross sectional area A. Let P be the pressure exerted by the liquid on the piston of cross sectional area A. That is, so as a result of that, the piston moves through a distance x. The piston moves through a distance x. Then work done is given by, that is, work done in moving the piston. Work done is given by, that is, force into displacement. Work done is equal to, we know that, force into displacement. So the work force is nothing but pressure into area. Pressure into area, cross sectional area. Pressure into cross sectional area, and distance moved is x. So the work done is PAX, and this work done is stored as the pressure energy. This work done is stored as the pressure energy. So that is work done is given by W is equal to P into A into X. A is cross sectional area, A is X is displacement. So you can write it as A into X as volume V. This is volume V, that is the volume swept by the liquid. The V is volume swept by the liquid, or volume covered by the liquid. So this work done is stored as the pressure energy. So therefore pressure energy of liquid of volume V, pressure energy of liquid of volume V, liquid of volume V is P into V. So P into V. So pressure energy per unit volume. So pressure energy of volume V is P into V. So now pressure energy per unit volume. Pressure energy per unit volume. Pressure energy per unit volume is equal to P into V divided by V, that is P. Pressure energy per unit volume is equal to P, that is excess pressure. And pressure energy per unit mass, now I will write pressure energy per unit mass of liquid. Pressure energy per unit mass of liquid, that is pressure energy divided by mass. So volume divided by mass, that is mass divided by volume is density. So that is called as P divided by rho. So you can write P divided by rho, that is pressure energy per unit mass of liquid. So now pressure energy per unit weight of liquid. Pressure energy per unit weight of liquid. Pressure energy per unit weight of liquid. Pressure energy per unit weight of liquid, that is pressure energy divided by weight of the liquid, that is mg. So volume divided by mass, that is nothing but density. So P divided by rho g. P divided by rho g. This is called pressure energy per unit weight of the liquid, and pressure energy per unit weight of the liquid is called as pressure head. It is called as pressure head. It is called as pressure head, and it is given by PV divided by mg. So that is P divided by rho g. That is called pressure head. P divided by rho g is called pressure head. This is pressure energy. A fluid having a streamline flow will have three types of energy: kinetic energy, pressure energy, and potential energy. So we have studied kinetic energy, and now we have studied pressure energy, and third one is potential energy. Third one is potential energy. Potential energy of fluid. So the energy possessed by the fluid by the virtue of its position, the energy possessed by the fluid by the virtue of its position is called as potential energy. The energy possessed by the fluid or liquid by the virtue of its position with reference to a fixed point or with reference to earth. The energy possessed by the liquid by the virtue of its position from the earth or from the surface is called as potential energy. And potential energy of a liquid of mass m is given by mgh. The potential energy of a liquid of mass m is given by mgh. And now potential energy per unit mass. Potential energy per unit mass of liquid. Potential energy per unit mass of liquid is given by gh. It is mgh divided by m. Potential energy per unit mass of liquid is gs. Potential energy per unit volume of liquid. Potential energy per unit volume of liquid, that is mgh divided by volume of liquid. Mass divided by volume, that is density, rho gh. So rho gh is called potential energy per unit volume of liquid. And then potential energy per unit weight of liquid. Potential energy per unit weight of liquid. Potential energy per unit weight of liquid, that is called as potential head. That is called as potential head or gravitational head. Potential head or gravitational head, and that is equal to mgh divided by mg. Now mg cancel, only h. So h is called as potential head or potential energy per unit weight of liquid. So understood? This is potential energy. So a fluid having a streamline flow, a ideal liquid having streamline flow possesses three types of energy: kinetic energy, pressure energy, and potential energy. Understood? Okay. So now depending upon this energy, so these energies are related by a equation. That equation is called as Bernoulli's equation. That is Bernoulli's theorem. So now we have to study Bernoulli's theorem. Understood? Okay. So now we shall study Bernoulli's theorem. That is, just now we have studied about the energy possessed by the fluid, flowing fluid, ideal fluid. So relating to that energy, there are great physicist by name Bernoulli has derived a equation, or related the energies of a fluid through a theorem called as Burlesque theorem. So now let us study the Burlesque theorem. So first statement. So according to Bernoulli, the sum of pressure energy, potential energy and kinetic energy. The sum of pressure energy, potential energy and kinetic energy per unit volume of fluid. The sum of pressure energy, potential energy and kinetic energy per unit volume will remain constant for an ideal fluid having a streamlined flow. According to Bernoulli, the sum of pressure energy, potential energy and kinetic energy per unit volume of fluid for an will remain constant for an ideal fluid having streamlined flow. So according to Burlesque theorem, for an ideal fluid having streamlined flow, the sum of pressure energy, potential energy and kinetic energy per unit volume will remain constant. That is, pressure energy per unit volume. Pressure energy per unit volume is P, and potential energy per unit volume. That is rho GH. Potential energy per unit volume is rho GH, and the sum of pressure energy per unit volume, potential energy per unit volume, and kinetic energy per unit volume. Kinetic energy per unit volume will remain constant for an ideal fluid having streamlined flow. So this is mathematically. So mathematically the expression for Burlesque theorem is given by, sometime they will ask this question for 5 marks and sometime they will ask for 2 marks. If they ask for 2 marks, write the statement and write this formula. 2 marks enough. Write the statement, write this formula, it is 2 marks enough. If they ask for 5 marks, state and explain Burlesque theorem, or state and derive the Burlesque theorem. Then you have to write the statement and then do the derivation. Just I will do the derivation, that is for 5 marks. Okay. So statement, what is the statement? According to Burlesque theorem, the sum of pressure energy, potential energy and kinetic energy per unit volume will remain constant for an ideal fluid having streamlined flow. For an ideal fluid having streamlined flow, the sum of pressure energy, potential energy and kinetic energy per unit volume will remain constant. So now let us prove this. To prove this one, consider an ideal fluid flowing through a tube of varying cross-sectional area. Consider an ideal fluid flowing. Ideal fluid means incompressible, non-viscous, incompressible fluid, liquid flowing through a tube of variable cross-section. Let this end of the tube is B and this end of the tube is C. I will call this as C end and this as B end. And the end B is at a height H1. The end B is at a height H1 and the end C is at a height H2 from the reference level or from the ground. Say this as a ground or this as a reference level. Okay. So now I am giving the proof of this Burlesque theorem. Proof of the Burlesque theorem. That is, we have to get that formula. Understood? Okay. So now let us consider a ideal fluid flowing through a tube of variable cross-sectional area. Here cross-sectional area is different, here cross-sectional area is different. And this end I will call it as B and this end I will call it as C. And the height of this end, that is average height of this end from the ground is H1 and the height of this end from the ground is H2. Let A1 be the cross-sectional area at the end B and P1 be the pressure at the end, pressure of the fluid at the end B. Similarly, let A2 be the cross-sectional area at the end C and P2 be the pressure at the end C, and V2 be the velocity of the liquid at the end C, and V1 is the velocity of the liquid at the end B. Let V1 be the velocity of the liquid at the end B, P1 and A1 be the pressure and cross sectional area at the end B, and let V2, A2 and P2 be the velocity of the liquid, cross sectional area of the tube and pressure at the end C. Understood? So now the work done in pushing the liquid, the work done in pushing a liquid of volume V, the work done in moving a liquid or pushing a liquid of volume V, liquid of incompressible liquid of volume V from B to C, from B to C. The work done in pushing a liquid of volume V from end B to C is given by the work done is equal to, that is work done is equal to work done at the end B, work done at the end C. So work done at the end B can be done as P1 V minus P2 V, where V is volume, So therefore you can write it as W is equal to P1 minus P2 into V. P1 minus P2 into V, where P1 is pressure at the end B and P2 is pressure at the end C. Okay. So now this work done is used by the liquid. A work has to be done to move the liquid from the end B to C. See here, end C is at a height and end B is at a lower height. So to move the liquid of volume V from the end B to C, the work has to be done, and the work done in moving the liquid or work done in pushing the liquid of volume V from the end B to C is given by W is equal to P1V minus P2V. You have studied this formula. Okay. So now this work done is used by the liquid in two ways. This work done is used by the liquid in two ways. First one, in changing the kinetic energy of liquid, in changing the kinetic energy of liquid from 1 by 2 m v1 square to 1 by 2 m v2 square. See here, when we push the liquid from here to here, the kinetic energy of the liquid will changes, because here velocity is v1 and here velocity is v2. So the kinetic energy of the liquid will changes, and this work done, the part of this work done is used by the liquid to change the kinetic energy of the liquid from 1 by 2 mv1 to 1 by 2 mv2. That is, change in kinetic energy is equal to, it is 1 by 2 m v2 square minus 1 by 2 m v1 square. 1 by 2 m v2 square, 1 by 2 m v1 square, or take common, 1 by 2 is taken common, m2 v2 square, m1 v1 square. Understood? This is change in kinetic energy of the liquid, change in kinetic energy of the liquid. And now the part of this work done is also used to change the pressure, potential energy of the liquid in changing the potential energy of liquid from where, from mgh1 to mgh2. That is change in potential energy. So change in potential energy delta PE is equal to mg h2 minus h1, mg h2 minus h1. See here, once again I will tell from the beginning. We are talking about Bernoulli's theorem, and I am giving the proof of Bernoulli's theorem. So for that, consider an ideal fluid. Consider an ideal fluid flowing through a tube of non-uniform cross-sectional area. Consider an ideal fluid flowing through a tube of non-uniform cross-sectional area. Understood? As shown in the figure. So now, let P1, A1 and V1 be the pressure, area of cross-section and velocity at the end B, and H1 be the height at the end B, and P2, A2 and V2 be the pressure, area of cross section and velocity at the end C, and S2 is the height at the end C. Now to push the liquid from the end B to C, a work has to be done. A work has to be done. The work done in pushing a liquid of volume V from end B to C. The work done in pushing a liquid of volume V from the end B to C is given by W is equal to P1V minus P2V. That is P1 minus P2 into V. This is work done in moving the liquid from the end B to the end C. And this work done is used by the liquid in two ways. This work done is used by the liquid in two ways. That is, first one, in changing the kinetic energy of the liquid. So when we push or when the work is done, that work done is used by the liquid to change the kinetic energy and also to change the potential energy, because kinetic energy and potential energy both are changing. So in changing the kinetic energy of the liquid, that work done is used, a part of work done is used to change the kinetic energy and remaining part is used to change the potential energy. So it is in changing the kinetic energy of the liquid from 1 by 2 mv1 square to 1 by 2 mv2 square. That is, change in kinetic energy of the liquid is this one. Understood? Final kinetic energy minus initial kinetic energy. And also the remaining part of the work done is used in changing the potential energy of liquid from mgh1 to mgh2. That is, change in potential energy is equal to final potential energy minus initial potential energy. That is mgh2 minus mgh1. mg taken common, h2 minus h1. Understood? And now, since the liquid is incompressible and ideal or non-viscous, so by the law of conservation of energy or by using work energy theorem, we can tell that work done is equal to the change in kinetic energy plus change in potential energy. So here there is a formula called work energy theorem. I think still you have not at all studied. That comes in the chapter called work energy power, that comes in the first part of the syllabus. Okay, so the work done is equal to the sum of change in kinetic energy and potential energy. The work done is equal to the sum of change in kinetic energy and potential energy. So therefore, how much work is done in moving the liquid from the end B to C, that work done is used to change the kinetic energy and to change the potential energy. Therefore, the change in kinetic energy plus change in potential energy must be equal to work done. That is, work done must be equal to change in kinetic energy and change in potential energy. And work done, we have work done as P1 minus P2 into V. And change in kinetic energy, we have 1 by 2 M2. Or here mass is constant, so mass is taken as constant. So then you can write it as M V2 square minus V1 square. Because a volume is considered to be constant. A fixed volume of liquid is moved from the end B to C. A given volume of liquid is moved from the end B to C. So therefore, a given mass of the liquid is moved from the end B to C. So therefore, I am taking M as common. Okay. So you will write the change in kinetic energy as 1 by 2 M V2 square minus V1 square. V2 square minus V1 square plus change in potential energy as mg h2 minus h1. H2 minus h1. This is from work energy theorem. According to the work energy theorem or according to the law of conservation of energy. According to the law of conservation of energy, work done must be equal to the change in kinetic energy plus change in potential energy. That also you can tell. So when we apply the law of conservation of energy, we get Bernoulli's theorem. Understood? We get Burlesque Theorem. So it is W is equal to delta Ke plus delta Pe. So now substitute these values and now make the some adjustment over there. So it is take this volume to this side. So then we will get P1 minus P2. P1 minus P2 is equal to 1 by 2 M divided by V. M divided by V is nothing but rho, that is density, 1 by 2 rho V2 square minus V1 square. right, plus m divided by v, that is also rho g into H2 minus H1. So now open the bracket, that is P1 minus P2 is equal to 1 by 2 rho V2 square minus 1 by 2 rho V1 square plus rho G H2 minus rho G H1. Now take H1, first term one side, it is P1 plus half rho V1 square, this side that becomes plus half rho V1 square, that is this side, that is plus rho G H1 is equal to, so or you can write just same as, so rho G H1 plus 1 by 2 rho V1 square is equal to 1 by 2 rho 1 by 2, that is P2. Take P2 term, two terms that side, that is minus P2 this side plus P2 plus rho G H2 plus rho G H2 plus 1 by 2 rho V2 square, 1 by 2 rho V2 square. So that is here. So this is nothing but pressure energy per unit volume, this is potential energy per unit volume, and this is kinetic energy per unit volume at the end B, and this is the sum of pressure energy, potential energy and kinetic energy per unit volume at the end C will remain constant, so that is P plus rho GH plus half rho V square will remain constant. So this is called as Bernoulli's theorem. Just now we have written this formula only. This is according to Bernoulli's theorem. Once again I will tell the definition differently. According to Bernoulli's theorem, the sum of pressure energy, potential energy and kinetic energy per unit volume will remain constant for an ideal fluid having streamline flow. That is the proof. Understood? And now further, this can also be written in different ways. This can also be told per unit mass also. Per unit mass. That is the sum of pressure energy, potential energy and kinetic energy per unit mass will remain constant for an ideal fluid having a streamline flow. Like that also you can tell. So that is Bernoulli's theorem per unit mass of fluid is given by, that is P divided by rho plus GH plus half V square will remain constant. So this is energy per unit mass. This is also Bernoulli's equation. This is the statement that pressure energy, potential energy, the sum of pressure energy, potential energy and kinetic energy per unit mass will remain constant for an ideal fluid having a streamline flow. And another way of explaining the same formula is, that is the pressure head, potential head and kinetic head. The pressure head, potential head and kinetic head, the sum of pressure head, potential head and kinetic head will remain constant for an ideal fluid having streamline flow. That also you can write. So that is given by the equation. So the same equation only I will write. Change this P divided by rho G plus H. So this is pressure head and this is potential head or gravitational head plus 1 by 2 V square divided by G, that is V square divided by 2G. V square divided by 2G will remain constant. This is pressure head, potential head and velocity head will remain constant. The sum of pressure head, potential head and velocity head or kinetic head will remain constant for an ideal fluid having a streamline flow. So these all are called as Bernoulli's equation. These all are called as Bernoulli's equation. This is also called Bernoulli's equation. This is also Bernoulli's equation. This is also Bernoulli's equation. This is per unit volume, this is per unit mass, and this is per unit weight, that is called head. In terms of head we will write. Understood? Okay. So this theorem, so very careful whenever you have to write the answer in exam. You have to make the answer according to the question. So, and see the marks. So, state and explain Bernoulli's theorem. If it is for 5 marks, then state the Bernoulli's theorem and derive all the things. Derive up to here, no problem. If it is for 5 marks. And the same question, state and explain Bernoulli's theorem for 2 marks or 3 marks. Then need not required to derive all the things, just to write the statement and then write the mathematical form with this little bit of explanation, then you will get 2 or 3 marks. Understood? So, as per the marks, make the answer. Understood? So, this is called Bernoulli's theorem. And now, so from this, so what we observe from this, if H is considered to be constant, if H is constant, then what happens? If H is taken as constant in this equation, so or any of the equation, if H is constant, then what happens? P divided by rho g plus V square divided by 2g will remain a constant. Will remain a constant. That is multiply by rho g. It is P plus rho V square divided by 2 will remain a constant. You can write like this also. P plus rho V square will remain a constant. So, now the liquid considered is incompressible, that is density is constant. So, it is pressure and velocity. The pressure and velocities are related. The pressure and velocities are related according to the Bernoulli's theorem. Understand this relation very carefully. Pressure and velocities are related by using the Bernoulli's theorem. So, that is if pressure is more, that is if pressure is more, the velocity of the fluid will be less. If pressure is more, the velocity of the fluid will be less. So, see here, pressure plus velocity both has to remain constant. If pressure increases, then velocity has to decrease so that it remain constant. This rho by 2 is a constant, okay. Rho is the density of the fluid and 2 is a constant, rho by 2 is a constant. A pressure is a number, any number Newton per meter square, and velocity is a number meter per second, consider just for our understanding. So, pressure plus this value will has to remain a particular constant. If pressure increases, then velocity should decrease so that it has to remain constant. Got my point? Think mathematically, we will get idea. So, that is if pressure increases, the velocity of the fluid will decreases. The velocity of the fluid decreases, then pressure will increases. If velocity of the fluid increases, then pressure will decreases. That means at a point where pressure is more, the velocity of the fluid will be less. At a point where pressure is more, the velocity of the fluid will be less, and at a point where pressure is less, the velocity of the fluid will be more, or vice versa, ulta. So, that is if velocity of the fluid is more, at that point pressure will be less. Velocity of the fluid is more, at that point the pressure will be less. If velocity of the fluid is less, at that point the pressure will be more. So, that is the relation obtained by the Bernoulli's theorem. That is the main understanding you have to get to understand further concepts of Bernoulli's theorem. So, in the next class we study the application of Bernoulli's theorem, and that application of Bernoulli's theorem you can understand only if you understood this equation. The application of Bernoulli's theorem you will understand only if you understood this point. Once again I will repeat this point. Remember properly. In the next class it will be very useful. So, from this equation we understand that rho by 2 is a constant. So, if pressure increases at a certain place, then velocity of the fluid at that point will decreases. If pressure of the fluid decreases at a point, then at that point the velocity of the fluid will increases. So, that is the relation. Understood? Okay. In the next class we study the application of Bernoulli's theorem.